Hello and welcome to this lesson where we will talk about scalars and vectors. One of the ways in which we can categorize physical quantities in physics is by stating whether that physical quantity is a vector or it is a scalar. So we want to start by defining a vector and distinguish it from a scalar. So the first objective in this lesson is to distinguish between a scalar and a vector. We want to know, is there a difference, and what is the major difference? We are usually asked to distinguish between a scalar and a vector in the exam. The other objective is that we want to state a few examples of scalars and vectors. We will also state the direction of a vector. We will look at different ways in which we can state the direction of a vector. We will also look at how we can represent a vector on a sketch. We are always drawing diagrams and indicating vectors on paper using various methods. We will look at how we can represent a vector on a diagram. We will add two vectors to get a resultant. And in this part, we will consider two vectors which are acting in the same direction. We will also look at two vectors which are acting in opposite directions. Two vectors which are perpendicular to each other, and two vectors which are acting at any other angle to each other. So let us go straight to the distinction between a scalar and a vector. By stating the definition of each one of them, we will have given the distinction. For instance, a scalar is a physical quantity which has magnitude only. The magnitude of a physical quantity usually consists of a number and a unit. That is how we state the magnitude of a physical quantity. We just state the number and a unit. For instance, length is equal to 5 meters. 5 meters is the magnitude of the physical quantity. You can see it has the number 5 and it has the unit meters. So the physical quantity we are talking about here is length. A vector, on the other hand, is a physical quantity which has both magnitude and direction. So it has two things: magnitude, which is represented by a number and a unit, and the direction. Now, we want to state here that if you're asked to distinguish between a scalar and a vector, just state the definitions. You will say something like this: while a scalar has magnitude only, a vector has both magnitude and direction, and that answer will be complete. Now let us look at examples of scalars and vectors. Examples of scalars include mass, distance, temperature, time, speed, and so on. In fact, all the 7 basic physical quantities, all of them are scalar quantities. Examples of vectors, on the other hand, include physical quantities such as weight, displacement, velocity, acceleration, and so on. Each time you come across a physical quantity in physics, you will be required to state whether it is a scalar or a vector, in addition to stating how it is defined. Now let us look at how a vector is represented. So we look at representation of a vector. A vector is represented on a sketch using a line segment with an arrowhead. The length of the line segment represents the magnitude of the vector, while the arrowhead represents the direction of the vector. So two vectors are the same if they have equal magnitude and act in the same direction. On the other hand, two vectors are different if either they have different direction but same magnitude, or same direction but different magnitude, or different direction and different magnitudes. Those are three ways in which a vector is different from another. So let's remember, a vector is represented with a line segment whose length is proportional to the magnitude of the vector, and the arrowhead shows the direction of the vector. There are, of course, several ways in which the direction of a vector could be given. One of them is just to indicate with the arrowhead. The arrowhead itself shows the direction of the vector. The other one is to use words like to the right, to the left, upwards, downwards, and so on. Another method is to give the bearing of the vector. You could even say something like, this vector acts in the southward direction, northeast direction, and so forth. That is, you could give compass directions. Another popular method in physics is to state the angle that the vector makes with a certain reference line. For example, you could say the force is acting at an angle of 20 degrees anti-clockwise from the horizontal. And this is the method that I'm going to use in the examples that I will give. I will state the angle that the vector makes with a given reference frame. We will see this when we come to it. So we have already looked at how we give the direction of a vector. An important section in physics is where we add two vectors or more to get a resultant vector. When we add two vectors, the sum is referred to as the resultant vector. There are several ways that we can use to add vectors. We are going to start with a very simple example. Let's assume we are given two vectors acting in the same direction. And here, I want to consider the vector force, because force is a vector. So we are going to add two forces which act in the same direction. Over here we have a grid, and let's assume we have this force here. This force. Let's assume it has magnitude of 10 units. And then we have another one acting on the same object, slightly displaced like that, but it has a magnitude of 15 units. This is the first force. This is F1 having a magnitude of 10 newtons. And this is the second force having a magnitude of 15 newtons. So we want to add them up. And the process is very simple. Every vector has a head. See, this one is a head and a tail. So F1 has H1 and T1, where H1 means the head of the first force. T1 means the tail of the first force. Of course, the second force here, F2, has got H2 and T2. When we add vectors, we usually follow a very simple process. We connect the two vectors head to tail. So I will take this force and bring its tail to the head of this one, so that I connect the head to the tail. And then the resultant, the sum of these two forces, which is 10 newtons and 15 newtons, is from the first tail here, this is T1, to the last head here, which is H2. All that. And we can see it occupies, this is 10 units, 15 units, and this is 25 units. So we can represent this using this force here, this single green force here, and you can see it starts from the first tail to the last head. So this is the resultant force. Now when we add these forces, it does not matter which one comes first. Let me return this one where it was. And now I want to start with this one. You see, I started with F1. Now I want to start with F2. And add F1 onto it. You can still see the resultant still remains the same. So F2 plus F1 is equal to F1 plus F2. So it does not matter which force you start with. You can start with any one of them. So when you are given two forces which are acting in the same direction, the process of adding them up is very easy. Just connect them head to tail. And it does not matter whether the forces are 2 or 3 or 4. Let's see this. We've got that force. Let me add another one here, and it will have a magnitude of 5 newtons, for example. So I've got 10 newtons plus 15 newtons plus 5 newtons. So the process is very easy. I just start putting them head to tail. So I'll bring this one here and bring this one here. F1 plus F2 plus F3. Connect them head to tail, head to tail, head to tail, and you have the resultant of 30 newtons. 10 plus 15 plus 5, 30 newtons. So it's just that easy. When you're given forces acting in the same direction, just connect them head to tail and get the sum. Like you can see here, the resultant is this green force here, which starts from the first tail to the last head. Provided you connect the forces head to tail, you will never go wrong. So that is how we add two vectors which are acting in the same direction. Let's now look at two vectors which are acting in opposite direction. How do we add them up? Now we are back to the grid. I'll get the first force just like before. It was 10 newtons. The next force acting on this object was 15 newtons, but this time I'm going to make it to act in the opposite direction. So I'm going to say that the object is somewhere around here, and there is this other force of 15 newtons acting in opposite direction. So you've got two forces acting in opposite direction. But notice that they have different magnitudes. This is a force of 15 newtons acting to the left, a force of 10 newtons acting to the right. How much is the resultant force? Again, here it is very easy to get the resultant force. Get one of the forces. Maybe let us say you are starting with F1. You add F2. How do you do that? Connect the head of F2 to the tail of F1. Like that. And I displace them sideways like this because I want you to see where I start from. Start from here, like that. And then I come and connect the head of F1 to the tail of F2. So this is where I started. I started here, I went this way, and then went this way, and stopped here. So my starting point is here, and my stopping point is here. So I just consider that straight line from where I started to where I stopped. And how much should be the resultant? It's very easy to see. This represents the resultant force. So we come and fit it in here. And you can see it is from the first tail to the last head. Again, the method of connecting the two forces head to tail works perfectly here. Let me repeat that so that you can get the idea clearly. I have two forces acting on a body here, but the two forces are acting in opposite directions. And these two forces have got different magnitudes. One has a magnitude of 10 newtons, the other one a magnitude of 15 newtons. I add them up to get the resultant force. I simply need to connect the forces head to tail. So I can get this force, slide it back like that so that its tail comes in contact with the head of this one. And I know this is where I started from, and this is where I stopped. I started from here and stopped here. So I draw a straight line from where I started to where I stopped. And remember, I'm putting them displaced like this, sideways, so that, when I put them together like this, you will not know. You see, one hides the other. So it's not very easy to know where I started and where I stopped. So I'm just displacing them sideways like that so that it is easy for us to see where I started and where I stopped. Just consider this line here to represent my origin, where I started, and this line to represent my destination, where I stopped. So the straight line distance from where I started to where I stopped becomes the magnitude of the resultant force. And the direction of that resultant force is very easy to get. It is from where I started to where I stopped. I put an arrow in that direction. And indeed, when we click this button here to give us the resultant force, you can see that the arrow, the green arrow, it does not matter whether the green arrow is here or there or there or even there. We are able to tell that the resultant has 5 units, which means 5 newtons to the left. Let's use some 2 other forces. Let's assume I have this one here. It's acting on the body in this direction. And then I have this other one here acting on the body in this direction. How much do you think is the resultant force of this system? F1 has magnitude of 25 newtons to the right. F2 has a magnitude of 10 newtons to the left. So let's arrange the forces head to tail. I can take this force, slide it backwards like that. And remember, when I do that, then this becomes the starting point. I slide it backwards like that. So I started here. I come join with this. I end here. This is where I started, and this is where I stopped. So how much is the resultant force from where I started to where I stopped? So the resultant is 15 newtons to the right. You can see how simple it is. Or, watch this. Instead of moving this, I now need to move F1. So this becomes my starting point. It becomes my starting point. The force which I don't move, its tail becomes the starting point. So I move this one until the forces are connected head to tail, like that. Over there. So I started here. I moved to this point and to this point. And you can see this is where I stopped. Again, how much is the resultant? See? 15 newtons. So again, it does not matter which force comes first. You can start with either, provided you remember, put the forces to be head to tail. Let's look at still another example of forces which are acting in different directions. So I have this force here, which has a magnitude of 10 newtons to the right, another one with a magnitude of 10 newtons to the left. How much is the resultant? Let's see. This is my starting point. So I connect that to that other point. This is my starting point. It is also my stopping point. And the resultant is 0. Because the starting point is the same as the point where I stopped. So the resultant force is 0. Now let's go to the next situation. So we have just seen how we add two vectors which are acting in opposite direction. How about if we are confronted with the two forces which are perpendicular to each other? By perpendicular, we mean they make 90 degrees with each other. How do we add them? Let's start with the object being in this position. So there is a force acting on it like that of about, we can say this one large box is 1 Newton. So 1, 2, 3, 4. 4 newtons to the right. And then we have another force acting on it 90 degrees to this one of 3 newtons, like that. Again, the process of getting the resultant is very easy. Just connect the two forces head to tail. So you get this one, you slide it like that so that its tail is connected to the head of this one. And then this is where we started, this is where we stopped. So we join our starting point to the point where we stopped with a straight line. Like that. And this becomes the resultant. This is 4 newtons, this is 3 newtons. How much is the resultant? Already you can see this kind of shape is a right-angled triangle because this is 90 degrees. So we can calculate the hypotenuse using 4 squared plus 3 squared, which gives us 25, is equal to the square of the hypotenuse. So the hypotenuse is going to be equal to the square root of 25, and you get 5 newtons. So the resultant here is 5 newtons at this angle from the horizontal or from the 4 Newton force. You remember the method we are using for giving the direction of a vector? We simply need to state the angle that the vector makes with a certain known direction. We know this force. This is the 4 Newton force. So you can say the resultant is 5 newtons at an angle of so much degrees. And if you work it out, you'll get this one to be 36.9 degrees. 36.9 degrees from the 4 Newton force. So that is how we can add two forces which are acting at an angle of 90 degrees with each other. Now let's look at the last part. Where we have the last part, we have two vectors which are acting at any other angle to each other. In other words, that angle is not 90 degrees. Neither is it 0 or 180 degrees. By the way, when vectors are acting in the same direction, the angle between them is 0. And then we have when they are perpendicular to each other. And when they are acting in the opposite direction, right in the opposite direction, the angle between them is 180 degrees. We will see that one in a moment. Now we are talking about vectors which are acting on an object, and the angle between them is any other angle other than 0, 90, or 180 degrees. Let us say maybe 45 degrees. We will understand this by using a grid. So we are back to our grid here, where we can have one of the forces. Let us say this is the force here. It has maybe a magnitude of, let's say, 4 newtons. And then we have another force at an angle of maybe 45 degrees, and it has a given magnitude. So here it is not very easy to tell the magnitude of this force because it is a hypotenuse here, but it's 2 and 2 here. So, but let us say we have a situation like that. We've got this force, and now we want to add these two forces to get the resultant. You can see that the angle that the two forces make is not 0, it is not 90 degrees, and it is not 180 degrees. Let me just explain what I mean by the angle not being 0. When we say that the forces are acting in the same direction, like this, these are two forces which are acting in the same direction. They have different magnitudes. I mean, these are two forces which are acting in the same direction. They have different magnitude. The angle between them is 0. We also looked at a situation whereby we have two forces which are acting on this body, but they are acting in opposite directions. Like that. We had a situation like that one a moment ago. The angle between them is 180 degrees. And in the last section, we just looked at two forces which are acting on a body, but the angle that they make with each other is 90 degrees. So you know how to add those ones. So here we use Pythagoras theorem. The other one we just add the forces naturally, and the other one we subtract the forces, so to speak. But how about if the angle is any other, like this? Let me return this force this point because I want more space to the right. How about if the angle is 45 degrees? Let's say something like that. How are we going to get the resultant? Again, this is not anything complicated. Just get one of the forces, slide it properly until it makes its tail comes in contact with the head of this force. Once you have that, then you know that you started here and ended up here. So the resultant must be the straight line from the point where you started to the point where you stopped. Like this. This one here. The length of this green arrow is proportional to the magnitude. So here we can use scale method. For example, you can, on a grid, you can draw a length of 4 centimeters. Then we come here, you draw a line of 45 degrees to the horizontal, and then draw a length which is proportional to the force that you are using here, and then join this point to this point. Measure the length of this arrow and use the scale that you used to get the magnitude. We will look at this one, this point, in the next lesson. At this particular point, I want to recap what we have done so far. We had set out to talk about scalars and vectors. And we have already seen how we can distinguish between a scalar and a vector. We have also seen some of the examples of scalars and vectors, and we have used the vector force. We have seen how we can state the direction of a vector, as well as how to represent a vector on a sketch. We have gone ahead and added 2 forces in order to get a resultant vector. And we started with 2 vectors in the same direction, followed by 2 vectors in opposite direction, 2 vectors perpendicular to each other, and finally 2 vectors which were acting at any other angle to each other. Now below this video, there are several exercises that I want you to undertake. Make sure that you undertake each one of them, because each one of them tests each of these objectives you see here. So if you find that a question is a bit challenging, just go through the video once again and I'm sure you will get the answer. Especially when it comes to objective 5, where I want you to add 2 vectors to get a resultant vector. If you get stuck at any one point, then just review the video, because I've gone through it step by step. And I'm sure if you watch the video several times, you will eventually get the point. So I will see you in the next video, where we look at now adding 2 forces which are acting at any other angle to each other using the scale method. Until then, have a nice time.